Hello students. So up until last class we saw the definitions of partition of a set, and we also looked into the Riemann integration and Riemann integrable functions, upper limit, lower limit sum, upper limit sum, and things like that. So today basically we will extend these concepts of Riemann integrable functions. There are some integrability conditions for a function to be Riemann integrable, and we will also try to look into fundamental theorem of integral calculus if time permits in today's lecture. So we in the last class we know that we saw that a partition P which is basically given by x0 x1 up to xn of a closed interval a to b, where such that a is x0 less than x1 less than x2 dot dot and up to xn is equals to b. So this is one such partition of the set of the closed interval a b. Now for this partition P we can define the norm of this partition. So the norm of this partition is defined as, so the norm of P is defined by the length of the greatest interval, greatest of all the subintervals, of all the subintervals xi to xi for I running from 1 to 3 up to n. So that means norm of P. So norm is usually denoted by this double bar notation. So norm of P is basically the greatest. So we can write as the maximum of x1 minus x0, x2 minus x1 dot dot xi minus 1 dot dot up to xn minus 1. So you can also write in short maximum over all I xi minus 1. So this is the way we define the norm of this partition P. You can also use a notation something like mu P. So we can write it as mu P, and the norm of the partition P can be denoted by this symbol mu P as well. So now that the definition of norm of this partition is cleared, we will look into one or two integrability condition, or to be very precise, Riemann integrability condition in this case. So let me start the new page. So the first one is, so Riemann integral as the limit of a sum. So this is this particular definition, or the representation of a Riemann integral will give motivation to the definite integral. So we will see that what do we mean by it. So the statement goes like this. So we can write a small theorem. So the theorem says that if f is a bounded and integrable, if f is a bounded and integrable function over the closed interval a comma b, then for every epsilon positive, there corresponds or there exists a delta positive such that for every partition P equals to A equals to x0, x1, x2 up to xn equals to B, of norm P less than delta, less or equal to delta, and for every choice of psi r x r minus to x r. So, we choose this point psi r in any rth interval x r minus 1 to x r. We have, what do we have? So, we have sum of all these f psi r times x r minus 1 minus integral from a to b f x dx is less than epsilon. So, what does this theorem actually say? So, this theorem says that if we have a bounded function f which is also integrable, Riemann integrable over the interval a comma b, then for every epsilon positive, so this epsilon is an arbitrary chosen small positive number, there corresponds a delta positive such that every partition, for every partition P whose norm is less than this delta, we can find a point psi r in these r intervals in the rth interval such that this value is less than epsilon. So, you see epsilon is an arbitrary chosen positive number. So, this integral is nothing but it can be expressed as the sum of this this f psi r times x r minus 1. So, this integral here, it can be represented as the sum of these f psi r times x r minus 1. The proof of this theorem is a little bit long, so we will not get into the proof of this of such theorems since it is a course meant for BSc and BTech students. So, we will not get into the proof, but the flavor of this theorem. So, what does it mean? I will try to explain that. So, let's look into this sum. So, let us write. So, let us look into this sum. So, let us write, let us say SPF. So, sum over the partition P for the function f. We write it as r running from 1 to n f psi r times x r minus 1. So, this sum where this psi r is any arbitrary point between x r to x r minus 1 to x r. So, the sum basically this sum, the sum SPF, the sum SPF is called the Riemann sum. I beg your pardon. So, this sum, is called the Riemann sum. Riemann sum of f over the closed interval a b with respect to the partition with respect to the partition P of the closed interval a b. Now, the above theorem can be seen in this following way, that if a function f, now the above theorem can be seen, or in other words it can be seen as, if a function f is bounded and integrable over the interval a comma b, then what we have is, we have integral, what we have is, we have integral from a to b, beg your pardon, f x dx is basically limit mu p, or the norm of p, going to 0, such that this limit SPF is actually the value of that definite integral. So, if you make the the norm of p going to 0, that means the norm of p or the the length of those intervals, when we say that it is going to 0, that means you are actually taking the number of subintervals as really small. And then in that case, if you look at this figure, let us say this is my f of x, and that is x equals to a, and that is x equals to b. So, doing this definite integral is basically, we are calculating this area. So, we are calculating this area if we are doing integral from a to b. Now, if I take the norm of p, norm of partition of p going to 0, that means I am basically making the number of subintervals really small and small. That means this n here and this n here, this number of subintervals are basically getting smaller, getting larger and larger. So, that means I am taking many really large number of subintervals. And if you take if you take your x1 here, then in that case what I am doing is this area here. This area here, it is basically if you take x1, if you take a really large number of subintervals, then in that case these small areas are actually converting into a rectangle. And here in this formula here, f xi r times xr minus 1, this is basically, if you forget about the summation, then this is basically the area of one such rectangle. So, you are actually dividing integral from a to b f x dx into some of the areas of really large number of rectangles. And if you sum all those areas of rectangles, then that will actually give you the integration from a to b. So, that when you make mu p goes to 0, you are actually making n tends to infinity. We are actually making here n tends to infinity. And if you make n tends to infinity, then basically you are increasing the number of subintervals, and then in that case this on every subinterval you are basically calculating the area of a rectangle. And if you sum all those areas, then that will give you the area of the curve of the function f between the points x equals to a to x equals to b. And that is what we mean by this integral on the right hand side. So, if you make n goes to infinity of this Riemannian sum, then that will actually give you the definite integral, or the integral of the function f between the points a to b. And this is the the vital point which we wanted to make, that how Riemann sum, how this sum here is related to the definite integral. So, the proof of the theorem is a little bit complicated, but you can be able to find the proof in any standard integral calculus book, where they have shown the proof with the help of upper sum and lower sum. It's not that difficult, and you can be able to go through that proof. However, for our lecture, we would try not to get into those details. But just to give you an idea how Riemann sum is related to definite integral, that's what I was trying to do. Now that we know how Riemann sum is related to definite integral, we'll jump to a new how to say, a new result, where we looked into where we look into the condition of integrability. So, condition of Riemann integrability. So, we can formulate this in terms of another small result. So, theorem 2, and it says that a necessary and sufficient condition, a necessary and sufficient condition for the Riemann integrability of a bounded function f is that for every epsilon positive, there exists a delta positive such that for every partition P of AB with norm P less than delta or less or equal to delta, we have UPF, which is our upper sum, minus LPF, which is our lower sum, is less than epsilon. So, that means if you are given a bounded function f, and if you would like to see whether that function is Riemann integrable or not, then we have to calculate the upper sum and the lower sum. In the last class, we have seen that how we calculate the upper sum and lower sum, and if the difference of the upper sum and lower sum is less than this chosen epsilon, then in that case that particular function is said to be Riemann integrable. This makes sense because the upper UPF, if you take the how to say, the infimum of all the UPF over the partition P, then in that case that will give you the lower integral sum, and that will give you the upper integral sum, and if you take the supremum of all such LPF such that for this partition P, then that will give you the lower integral sum, and the difference, basically we say that the function is Riemann integrable when the lower integral sum and lower integral sum and upper integral sum are same. So, basically if you say that the difference is less than epsilon, that means the function is Riemann integrable and your lower integral and upper integral are same. So, in a way this condition actually makes sense, and based on which we can say that the given function is Riemann integrable or not. Next we have is So next we have is several properties of a Riemann integrable function. So for example, we know that if a function is bounded, then if it satisfies this condition UPF minus LPF less than epsilon, then it is Riemann integrable. What other properties the function needs to have if you want to say that whether the function is Riemann integrable or not. So we will look into a few properties and how to say some results related to Riemann integrable function. So let's go to the first property. So I can write it as properties of Riemann integrable functions. So the first property is, or you can write it in terms of as theorem. So the first property or the first theorem in this regard is every continuous function, every continuous function, every continuous function is Riemann integrable. So this makes sense because every continuous function is always bounded, and if the function is bounded, then all we have to show that whether the UPF minus LPF is less than epsilon or not, and if it does, then in that case the function is Riemann integrable. The proof is a little bit how to say, well, it's not long, it's just that for the proof you can look into any books. Here I'm just how to say listing some of the important properties of Riemann integrable functions. For the proofs, I would recommend to look into the references which I have shown you in the first class, and there you can be able to find the proofs of these theorems. The second property is if a function f is monotonic on the closed interval AB, then it is Riemann integrable. So I am hoping that all of you know what does a monotonic function mean. So a monotonic function f, a function f is said to be monotonic. So a function can be monotonically increasing or monotonically decreasing, or it can be strictly increasing or strictly decreasing. So here monotonically increasing on AB if if fx1 is greater or equal to fx2 for x1 greater or equal to x2, where x1 and x2 are both 2 points in AB, monotonically increasing. And similarly we can define the monotonically decreasing part. So a function is said to be monotonically decreasing, so it is said to be monotonically decreasing if fx1 is less or equal to fx2 for x1 greater or equal to x2, where x1 and x2 are 2 points in this interval AB. So here we can see that if a function is monotonic, so let's assume that it is monotonically increasing on this closed interval a comma b, then in that case of course it is bounded, and if it is bounded, then all we have to show is that whether UPF minus LPF is less than epsilon or not, and then that will ensure the Riemann integrability. Similarly, we can assume that the function is monotonically decreasing, and if it is monotonically decreasing, then of course in that case also it will be bounded, and we again try to show that UPF minus LPF is less than epsilon, and then the function will become Riemann integrable. So the proof of this theorem can also be found in those books which I have listed as reference. Next property is I can list it as let's say theorem 3. So if f is a Riemann integrable function on AB, and C is any arbitrary point between the interval a comma b, then f is Riemann integrable on a to c and c to b, and we can write the integral from a to b fx dx as the sum of these two integrals. So that means you can take as many points as you please in your integral in your closed interval a to b, and the sum of those integrals on each one of those subintervals will be the integral of the whole of the function f on the whole interval a to b. So here not only c, you can take as many points as possible in between that interval a to b, and the result would still be true. Next theorem we have, or the property we have, is if a function f is Riemann integrable on the closed interval a comma b, then f square is also Riemann integrable. So if you have, and similarly you can continue. So if f square is Riemann integrable, and then in that case you can be able to show that f cube or f to the power 4, they are also Riemann integrable. So that means this property carries forward. And again, for the proof of this theorem, I would recommend you to look into the references which I have mentioned. Next, so as we have seen that for the Riemann integrability, how we can connect the Riemann integrability with the Riemannian sum, and how it is connected with the definite integral. We also saw that the necessary and sufficient condition for a function to be Riemann integrable, and some properties associated with Riemann integrable function. So we'll stop this lecture at here, and in the next class we will again continue with the properties of Riemann integrable function. Thank you.